I'm doing simulations of stabilized flames using PeleC. This is part of the Exascale computing project. If you were here last year, you may have seen a talk from Oak Ridge about the work underway at national labs around the country on these codes, and we're excited to be using Pele to do some simulations on blue waters. So I'm going to start by telling you exactly what the problem is that we're trying to address, and that's loss of stable combustion. Here we have a rather extreme example. This aircraft failed rather catastrophically, and you can see a flame just shooting out the back there, which resulted in total failure. So maintaining stable combustion in these sorts of systems can be a challenge, and we're going to use this sort of aircraft configuration as a example throughout the talk of our target case. Similar configurations can be found in power plants as well. Just keep that in mind. So what we intend to do is to use flow dynamics naturally occurring in these systems to keep the flame stable. And you can think of this similar to the way that if you toss a stick or a soda can into a stream, if you have a rock in that stream, you create eddies in the back of it, and you keep your stick or your soda can or whatnot. In just the same way, if we have a bluff body, a cylinder, a sphere, a prism in these flow fields, the flame will actually stay in that recirculation zone right behind, or at least that's the hope. It's not always a surefire solution, and that's what we're trying to fix. So accurately capturing the physics of these recirculation zones in combusting systems is an ongoing challenge. A lot of teams are working around the country to use lower order, reduced order models, LES, Reynolds average, Navier-Stokes equations to solve this problem. But we're looking to use higher resolution simulations, and we're using blue waters to start this off. So to delve a little bit more into the physics of these recirculation zones and how flames get trapped behind them, imagine here or envision flow coming in from the left-hand side. So you have combustion or reactants coming in from the left-hand side of the field here. You have a triangular prism, which is actually extending out of the plane in 3 dimensions here. And you have the flow then coming off the bluff body in shear layers and recirculating the low pressure zone, just like in a stream with a rock behind it. It gets trapped here in the recirculation zone. Further downstream, you have larger von Karman type oscillations you might remember from fluids class. And the shear layer vorticity rolls up into those oscillations. In the combusting system, the flame actually lives in the shear layer. So you have the reactants coming in from this left-hand side, and the hot gases in the recirculation zone ignite them in the shear layer. And that's where the combustion lives. So the target case that we're simulating is an experimental case under active investigation at the Air Force Research Laboratory. These images here are results that they presented at SciTech this year. What we have here, this little red object, I know it's very, very small on this screen, is that triangular bluff body. So that's our solid object in the stream. You have flow conditioned upstream of it, coming in from this direction and igniting right here. That flame gets trapped behind this bluff body, and you get these flames here. The recirculation zone is going to be right over here in each case. So one of the issues that we're looking to address with blue waters is incongruities between the experiments and the computations that have been done so far. We're looking at a kind of span of experimental computational domains, and we're trying to analyze those against the experimental data to see what shortcuts we can take, what physics, what boundary conditions we actually need to use to capture these physics. So you have here on the left an old picture from the 1950s of a top-down view of one of these stabilized flames. And what you can see, what we have here is on the top and bottom of the screen are solid walls. You can see that the effects of these solid wall boundary conditions are actually propagating into the middle of the stream. This is important because a lot of simulations to this day ignore these walls and just simulate the center with periodic conditions. So we're doing two things. We're looking at a span of periodic boundary widths. So we're going to look at just a tiny slice of periodic simulation domain representing the middle here, and then wider periodic domains. And we're also looking at wall-bounded simulations. I don't have images from that today, but I'm happy to talk about it if you would like. So about our computational code, as I mentioned, we're using PeleC. This is under active development at AMReX in Colorado, right near us at the University of Boulder, as well as Lawrence Berkeley and a bit at Argonne as well. The intent here is to do direct numerical simulations of turbulence chemistry interactions, and it has device modeling capabilities through the embedded boundary framework. That's a cut cell approach in the finite volume physics or mathematics that are used. This code also uses adaptive meshing to provide localized refinement. What that looks like, imagine here you have a flame coming up out of the ground. Basically, you have a little rod around which that flame is stabilized. And we can basically grid at different levels. So green here in this simulation represents the coarsest level of gridding. We have then finer gridding in pink and a simulation of the flame in blue. So this allows us to devote computational resources only where we need them. And we see order of magnitude speed-ups over static refinement. So this is what allows us to span simulating entire engineering relevant domains and getting down to those tiny little physics that we're hoping to capture. So I'm going to share mainly here non-reacting results. We're working on getting stable combustion. I'll touch on that briefly at the end. So what we're starting to look at on blue waters is how much of this adaptive refinement do we need, and then also how much of that domain width do we accurately need to capture in order to simulate the stabilized flame. So just to give everyone kind of a sense of how much computational resources we're spending here, we're running these cheapest simulations on just 4 nodes, and they take about 100 node hours to run. The most expensive ones, we've gone up to 80 nodes. These runs are costing around 20,000 node hours. We have good scaling in this range, but we haven't really pushed the boundaries on that scaling blue waters just yet. It is limited also by the refinement criteria that you choose. If you can imagine choosing, say, temperature, vorticity to refine on, you might not be able to exactly predict how large your computational domain is going to be. So that puts some limits on how perfect scaling you can implement ahead of time. So this is what the gridding looks like. Here we have, again, flow coming in our imaginary jet afterburner configuration. From the left-hand side, we have these reactants. And right now, they're just flowing around here without combusting. And the red shows higher vorticity magnitude. So you can see that with this adaptive refinement, we're getting much higher local resolution. I will also point out that each of these black boxes represents, on average, 16 cubic cells. So I'm not showing cells here, I'm showing grids, which is how the domain is decomposed for MPI parallelization. The AMReX AMR framework does allow for MPI or OpenMP parallelization as well, but we haven't implemented that just yet. So looking at just the flow physics for different levels of refinement, then to understand how important each of these levels can be. These are very coarse simulations here. You see very little refinement on the top, more refinement on the bottom. If we move on to our even finer resolutions that we've gone to, we see much more intense vorticity, and actually we see a characteristic change in those recirculation zones that we care so much about. So you can see in these simulations, we have very intense vorticity penetrating the recirculation zone region and a reduction in size of that region as well. So overall, the vertical flapping motion here changes those recirculation zone dynamics, which we actually care so much about for the stabilization of our flame. And we're going to look at some statistics here. We have time average velocity fields. This is just the two-level refinement case. We're going to look at the statistics along the center line to understand those recirculation zone length changes. So that's what those dashed lines show. These are our statistics at this point. We have a probability density function in the upper left taken from that recirculation zone. We have mean velocities, standard deviation, and skewness. You can see, like I mentioned, this recirculation zone, which is represented by negative velocities relative to the inflow, is shortened for those 3 and 4 level cases. And then for the higher refinement as well, those 3 and 4 level cases, we see a higher standard deviation. We're still collecting more data to try and converge these statistics more fully, but these are the trends that we're seeing so far. We're also looking at aspect ratios, as I mentioned, to understand how much of that domain we need to capture. These are all the same level of refinement, 3 levels. So they're all the same physical resolution. And so far, we're not seeing a whole lot of change in each case. Slightly higher turbulence, slightly higher standard deviation in the smaller domains, actually, which goes contrary to what we expect. You would expect with the higher aspect ratio that you would allow for more development of turbulent structures in all 3 dimensions. So we're a little confused by that and looking to investigate it more as we move forward. So I mentioned that we're working on getting combustion going. This is a little bit more of a challenge with the AMR codes than it is for static refinement. Currently, we're seeing some numerical instabilities at the boundaries of the AMR grids as the combustion propagates through them. So that's what we're working on currently. And I've been checking right up until about half an hour before this talk. I think I have a stable simulation going, so maybe if you had me give the talk tomorrow, I would have had full results for you. So that's a little unfortunate, but I am excited that it's finally seeming to work. So in summary, we're using adaptive mesh refinement to provide local resolution where we need it, and that's helping us speed up these simulations, comparatively cheaper cost relative to a full static refinement. We're seeing that 3 levels of refinement is absolutely necessary to capture the shear layer and recirculation zone dynamics that we're interested in. We're seeing little difference between aspect ratios for our cases, which is surprising. And I mentioned an ongoing area of investigation. And then working on combustion actively and in a very excited fashion. I would like to thank the Blue Waters and NCSA for graduate fellowship, which has fully funded this work. Here's a couple citations from images I shared throughout the talk, and I would be happy to take any questions.